Hi, my chemistry review project will be on atomic notation and predicting geometric and molecular shapes. So for those who are wondering, this topic was taken from Unit 2, which was called Structures and Properties of Matter. So let's recall the VSEPR theory. The valence shell electron pair repulsion short-term VSEPR theory states that molecules will adapt the shape that's lowest in energy. This also means that each specific compound will have its own distinct molecular shape. In addition to this, the VSEPR theory primarily focuses on valence electrons and their repulsion and only deals with pairs of electrons that can be lone and bonded. When you look at a VSEPR diagram such as the one right here, you can see that there are electron regions around the central atom, which are right here and right here. These electron regions can also be known as electron pairs or bonded pairs. So since both regions are negative, they tend to repel one another, so they would go like this and like this. But since the central atom is still positive, they would still be held together in a certain shape. So this leads to distinct geometric and molecular shapes for different compounds. So from this information, we can conclude that there are 5 main geometries and also a variety of molecular shapes that these geometries can appear in. So let's take a look at the 5 main geometries. The basic geometric shapes of compounds have 5 different variations based on the number of bonded pairs. A bonded pair is a pair of electrons involved in a covalent bond. So if you look over here, the names of the 5 main geometries are given. So when a compound has 2 bonded pairs, its geometry would be linear. When there are 3, it would be trigonal planar. When there are 4, it would be tetrahedral. When there are 5 bonded pairs, the geometry would be trigonal bipyramidal. And when there are 6 bonded pairs, the geometry would be octahedral. When considering bonded pairs, it is also really important to know that a single bond, double bond, and triple bond will always end up equaling 1 bonded pair. This diagram can give you a basic rundown of the general shape of each of the 5 main geometries. Each of the balloons represents 1 bonded pair, and the central atom in the middle is represented by the knot that connects all the balloons. So if we use tetrahedral, for example, you can see that there are 1, 2, 3, 4 bonded pairs in tetrahedral, and it is connected by the central atom in the middle. If you look below, you can see that the tetrahedral geometry has an angle of 109.5 degrees, and which means that each geometric shape also has specific angles, and these angles can vary even more based on their molecular shape that I will get into after. It is also very important to note that you need to memorize all 5 of these geometries as they will not be given on the exam. So again, the 5 main geometries are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Now let's get into molecular shape. When considering VSEPR diagrams, some compounds will have lone pairs. As a result, their overall shape will not be the same as their geometry, and this results in a different shape called the molecular shape. A compound will have a different molecular shape than its geometry when it has lone pairs. If there are no lone pairs in the compound, the molecular shape will be the same as its geometry, and the molecular shape will basically be the geometric shape. The importance of molecular shape. The shape of a molecule plays a big role in determining its properties, and these properties include the taste and smell of a substance. So if you look to the right, you can see that each of the 5 main geometries has a distinct molecular shape based on the number of lone pairs that a compound can have. Now that we know about molecular shape, let's look at the number of lone pairs that determine the different types of molecular shapes for each geometry. If you look at the first row, you can see that there are 0 lone pairs. So as a result, the molecular shape will be the same as its geometry. But if you look at another row, such as this one right here, you can see that since there is 1 lone pair, the molecular shape would be different from the geometric shape. This chart tells you the different types of molecular shapes each geometry has based on the number of lone pairs of a compound. An important side note is that when considering a compound's geometry and its electron pairs, it is crucial to count both the lone pairs and bonded pairs so that you can get the right geometry. Also, shout out Miss Rowe for the chart that I took from her PowerPoint. Now let's turn our attention to VSEPR notation. So there are 3 letters in the VSEPR notation, which are A, X, and E, and all 3 of these letters represents a certain part of the VSEPR diagram. So A represents the central atom, X represents the bonded pairs, followed by a subscript that represents the number of bonded pairs, and E, which represents the lone pairs, which are non-bonded, and also followed by a subscript. This notation goes in the order of A to X to E. Now let's try an example. This question asks, what is the VSEPR notation, geometric shape, and molecular shape for this compound right here? So since there are 3 electron pairs, 1, 2, and 3, the geometry of this compound is trigonal planar. The VSEPR notation is AX3, where A is this right here, X3 is represented by all 3 of the bonded pairs. The molecular shape is the same as its geometry because there are no lone pairs on the central atom. Now let's take a look at another example asking the same question of what is the VSEPR notation, geometric shape, and molecular shape for this compound right here. So as you can see, this compound is actually different from the other one because there are lone pairs of electrons. So since there are 6 electron pairs represented by 2 lone pairs and 4 bonded pairs right here, 1, 2, 3, 4, 5, and 6, the geometry of this compound would be octahedral. The VSEPR notation would be AX4E2, where A is the central atom, xenon, Xe, X is the 4 bonded pairs right here, and E is represented by the 2 lone pairs. So since there are lone pairs in this compound, the molecular shape is different from the geometric shape, and if you look back at the chart, when there are 4 bonded pairs and 2 lone pairs and an octahedral compound, the molecular shape would be square planar. So that would conclude this review video, and thank you all for watching.